Hey guys, so we're going to start looking at parallel circuits. We saw series circuits last week. So parallel and series basically just has to do with how the components are connected. So when we saw a series circuit, we saw that in that case the current has only one route to follow. Okay, the current doesn't split at any point to go through any different components. With a parallel circuit, this is when you have a closed circuit where the current does split to follow multiple different pathways. Okay, now I know this diagram looks a little bit complicated, so I'm going to just in red show you where the actual circuit is. Okay, so our current is going to leave our battery and move here. When it gets to this point, it is then going to split. Some of the current will go up to resistor 1, and some of the current will go up to resistor 2. Okay, it will go through the resistor and the ammeter there, through the resistor and the ammeter there, and then the current comes back together at this point, goes back to our battery. Okay, so everything that is still black is the current doesn't actually flow there. Okay, so the voltmeter, again, like I said in the previous video with series circuits, it's got such a high resistance that almost no current will come down this way. Okay, it's a negligible amount of current, so we don't really need to include it in as a pathway for the current to flow. Okay, so our current is going from our battery out. Okay, it splits here, goes through each of our resistors, through each of our ammeters, and then joins back up together over there, and then it goes back into our battery. Okay, now we saw with series circuits, I hope you can remember the three things. With series circuits, current was the same everywhere, potential difference was divided amongst the components, and resistance, if you wanted to know the total resistance, you summed up the resistance of each of the resistors. Okay. So now we're going to see with a parallel circuit, how are those three things affected. Okay, starting with current. Oh, I forgot how to spell current. 2 R's, sorry. Okay, so starting off looking at current. The current in a parallel circuit behaves in the way that the definition sort of tells us it does. We know that the current splits. Okay, our current moves from our battery, and at this point it splits. So whatever the current was here, that is going to equal the sum of the current here and here. Okay, so the sum of the currents in the two branches equals the current actually being dissipated by the battery. So just like with a series circuit, we call the series circuit a potential difference divider. A parallel circuit is a current divider. Okay, so that is on your notes. I'm not writing it just like with the last one. I'm just going to write down the maths part. But very important that you understand that the current, the total current coming out of the battery is still the same, still the same, still the same. At this point, it splits. Okay, so the current in this branch and the current in this branch together will make up the total current. Now, also very important, it does not split equally. It splits according to the resistance in each branch. Okay, now the current wants to take the path of least resistance. So if R1 had more resistance than R2 did, then that would mean that more current would go the way of R2 and less would go the way of R1. Okay, so the current splits so that more of the current goes where less of the resistance is. So please don't tell me if you know the current here, you're just going to halve it. No. Okay, it's not going to be half and half. Okay, so actually doing the math, the current, I'm going to call it the total current. What I mean by that is the current going through the battery. Every time I talk about total, we're basically saying for the whole circuit, which is the same as just for the battery. So the total current, or the current going through the battery, is equal to the sum of the current in each branch. So I'm going to call this one branch 1, and I'm going to call that one branch 2. Okay, so the total current, the current going through the battery, will equal the current in branch 1 plus the current in branch 2. Okay, then next up we need to look at how does potential difference be affected by your resistors being connected in parallel. Okay, so this now is kind of the opposite of current. So if we think back to series circuit, the current was equal everywhere and the potential difference was divided. In a parallel circuit, the current is divided and the potential difference is equal. Okay, so what that means is the potential difference of your battery is going to be equal to the potential difference in this branch, which is equal to the potential difference in that branch. Now we're not there yet, but notice that I'm saying branch and not resistor, okay? The potential difference over this resistor is not necessarily equal to the potential difference over this resistor, because we could have a third resistor in this branch. We don't, okay? We're not there yet, but I'm just saying, note I'm saying branch and not resistor. The potential difference in this branch is equal to the potential difference over this branch is equal to the potential difference of our battery. Okay, so potential difference, V total, the terminal potential difference, the potential difference of the battery, is equal to, now I'm going to say VP, okay, that means V parallel, so the potential difference of the parallel section. I'm saying that because right now we only have a parallel section, but later on I could put another resistor over there, which is now in series with those. Okay, so the total potential difference, the potential difference of the battery here, is equal to the potential difference of the parallel combination, which is equal to the potential difference in branch 1, which is equal to the potential difference in branch 2. Okay, the potential difference here, same as there, same as the whole potential difference, same as the potential difference in the battery. And then the last one, the resistance. This one is pretty cool. Okay, you'll see in your notes, it says there, I'm paraphrasing, but something along the lines of adding resistors in parallel decreases the total resistance. So it sounds a little bit weird, but let's just look here. Let's say I had a circuit, okay, like this, and it had one resistor in there, okay, of 2 ohms. If I were to add another resistor in series over here, that's another 2 ohms. You agree I've now changed the total resistance to 4 ohms. It was 2 ohms, now it's 4 ohms. Okay, when you add in series, you increase the total resistance. But if I took this 2 ohm resistor and instead of adding it in series, I added it in parallel, so let's say I made the current split here and go like this, then what I've done here is I have actually decreased the total resistance. The resistance was 2 and now it is, and now it's 1. Okay, I'll show you how to calculate that in a second. So there the resistance was 2, and now I've added another resistor, but now I've done it in parallel. I've brought down the total resistance. Okay, please remember that. The more resistors you add in parallel, the more you bring down the total resistance. Okay, so then just mathematically, the total resistance, or the equivalent resistance of our circuit, we calculated using a 1/over relationship, because remember 1/over something means it's inverse proportion, and that's what we see with resistors in parallel. The more resistors you add, the smaller the total resistance gets. So 1/over R total equals 1/over R1 plus 1/over R2, etc. Okay, and then I'm going to add this to here. I think it's in your blokkie. Okay, in your block it just says remember to invert your final answer. I'm going to show you what I mean by that. So if we were working out our total and we substituted numbers in here, what you would do at the very end, so let's just put a 1 and a 2 in there. Okay, so we're just doing a little example of what I mean by invert. Okay, so 1/over R total. Let's say R1 had a resistance of 1 and R2 had a resistance of 2. Okay, then we would add these fractions together. You can either do it using remembering how to add fractions from grade 8, doing LCD, all that nonsense, or you could just use your calculator. So this is going to be 3/2. Okay, we'll have 1/over RT equals 3/2. And now we don't want 1 over the total resistance, we want the total resistance. So what I want you to do after this, I've not left enough space, you're going to then write R total equals, and you're going to invert this, and by that I mean you raise it to the power of -1. Okay, so on your calculator, you're going to have your fraction 3/2 and raise it to the power of -1. That's how you invert it. It's easy to invert this one without doing the -1. Invert just means turn it on its head, eh? But sometimes at this point you're going to have a weird decimal. You're going to have something like 0.63294. That's hard to invert without using to the power minus 1 because it's not a common fraction. Okay, so you'd invert it using it to the power of minus 1 if you had something scary that you couldn't just do through observation. And then you would say, well, that means RT is equal to 2/3, and then you would change it to decimals. Okay, 2 decimal places. Okay, so that's how you would set out your answer for this. You write your formula, obviously, you substitute in, and then when you get to the part where you don't want 1 over R total anymore, you just want R total, you show that you are inverting it by raising it to the power of minus 1. Okay, and then once you've done that, you convert it to a decimal fraction using 2 decimal places. Got it? Okay, yeah, that's it. So quickly go over it again. Current, the current going through the battery is equal to the sum of the currents in each branch. Okay, the potential difference over the battery is equal to the potential difference of this whole thing, which is equal to the potential difference of each branch. And then resistance, because when you add resistors in parallel, you bring down the total resistance. We use this 1 over relationship, okay, inverse relationship. So 1 over R total is equal to the sum of 1 over the resistance of each of the resistors. Okay, and remember for this as well for LCD, if you aren't using your calculator or if you can't use your calculator for some reason, remember when you add fractions, you need an LCD. Okay, yeah, so that's it for the notes. I'm going to pause you there and we're going to do a quick example. Okay guys, it looks a little bit scary, sorry, there's quite a lot going on. So we've got our circuit in the middle here, top middle of the board. Okay, let's quickly look what's going on. We've got a battery, we've got followed by an ammeter. We get to this point and the current splits into 2 parallel branches. In our top branch, we have an ammeter and a light bulb. In our bottom branch, we also have an ammeter and a light bulb. Okay, then the current comes back together again through another ammeter and back to the battery. Okay, and it's going to keep going around like that. Now, in the question, always please read above or below, read all around the circuit diagram. A lot of important information is hidden in the words. Okay, so in the words on your worksheet, it tells us that the potential difference of that the resistance of bulb 1 is 12 ohms, that the resistance of bulb 2 is 4 ohms, and that the reading on ammeter 2 is 3 amps. Okay, so that was given to us in the question. Then, question 1, determine the total resistance in the circuit. So we have a look at our circuit. We see we only have 2 resistors, okay, they're light bulbs. We only have 2 resistors, and those 2 resistors are in parallel. So because we have resistors in parallel, to determine the total resistance, we would either have to use 1 over R total equals the sum of 1 over each of the resistors, or Ohm's law is always in your back pocket as well. So to use Ohm's law, we want total resistance, so that means we need to know total potential difference and total current. We know neither of those things. So we're going to have to go ahead and use the root of 1 over R total. Okay, so we're going 1 over R total equals 1 over R1 plus 1 over R2. Okay, that means 1 over R total equals 1 over 12 plus 1 over 4. Okay, you add them together using your calculator. Mine is under the couch. Okay, hang on. Okay, so that's going to be 4 over 12, which is 1/3. Is that right? 4 over 12 plus 3 over 12 is 4 over 12, which is 1/3. Okay, so we get that R total is 1/3. So to find, or 1 over R total, sorry, is 1/3. So to find R total, we say that that is equal to 1 over 3 to the power of minus 1, which when you go and do that, you actually get 3 on the dot, 3 ohms. Okay, so the total resistance in the circuit is 3 ohms. Question 2, determine the potential difference over bulb 1. Okay, so we want to know the potential difference over this bulb over here. So we've got again options. We can either use the fact that we know the potential difference over the battery will be equal to the potential difference in this branch, but we don't know the potential difference in the battery, so that doesn't help us find the potential difference in this branch. So the other option always is we could use Ohm's law. For Ohm's law, it's those three variables. You need to know two of the three at that component. So at bulb 1, I know the resistance is 12 ohms. Now we've got to think back to series circuits. If the current over here is 3 amps, between this ammeter and this bulb, that current hasn't split. So whatever the current is at this ammeter, it's equal at that bulb. So I've got the resistance and I've got the current at bulb 1. So I can use Ohm's law to find the potential difference. Okay, so I can say there at bulb 1, I'm using Ohm's law. V equals IR. We substitute in, we're looking for V, so that's going to be equal to the current, which is 3, times the resistance, which is 12, and we get 36 ohms. Okay, so the, potential difference, 36 volts. Okay, so the potential difference over bulb 1 is 36. Okay, question 3. Determine the terminal potential difference. Ooh, okay. So here it's, okay, again, we could use Ohm's law. We do know our total, but we don't know the total current. So we know the current here is 3 amps, but remember, this current split. So 3 amps went this way, but we don't know how many amps went this way. So we don't know how much current is going through the battery. So we can't use Ohm's law. So instead, we're going to use our understanding of how potential difference behaves in a parallel circuit. And that is that the potential difference of each branch is equal and is also equal to the potential difference of the battery. Okay, so for terminal potential difference, we can say Vt is equal to the potential difference in branch 1, which is equal to 36 volts. Okay. Question 4. Determine the potential difference of bulb 2. Again, okay, so at bulb 2, we could use Ohm's law. We could use the fact that the potential difference over bulb 2 would equal the resistance there multiplied by the current going through it, but we don't know the current going through here. We know 3 amps are there, we don't know how many amps are down here in this branch. So we can't use Ohm's law, so instead we look, what do we want? Potential difference. How does potential difference behave in a parallel circuit? It's the same in each branch. So if the potential difference in branch 1 was 36 volts, then the potential difference in branch 2 must also be 36 volts. So V2 is equal to V1, which is equal to 36 volts as well. Okay, question 5, determine the current through bulb 2. Okay, so always you have two options for every question. You either use Ohm's law or you use your understanding of how that specific thing works in that specific circuit. So we've got a parallel circuit. We need to determine the current through bulb 2. So if we were to use our understanding of current in a parallel circuit, it would be that the current out here splits and is then equal to the sum of the current there plus the current there. Now we don't have enough information. All we know is we've got 3 amps in this branch. We don't know anything about the current out here. We don't know anything about the currents in this branch. So we can't use that. So we use the other option, which is Ohm's law. Bulb 2, we know the resistance. We know the potential difference. We just worked it out. It's 36 volts. So we can use Ohm's law here. We can say V is equal to IR. Potential difference was 36 is equal to the current, which is what we're after, times the resistance, which is 4, and then we divide 36 by 4, and we get that the current is 9 amps. Okay, question 6, determine the reading on A1. Okay, so this is A1. This reading on A1, do you agree with me, will be the same as the reading on the battery, right? It's the current going through the battery, it's staying the same current, and here it splits. Now we know we've got 3 amps there, and we've just worked out we've got 9 amps here. So do you agree with me, I must have a total of 12 amps. Okay, the 3 amps and the 9 amps split from something into 3 amps and 9 amps. So this must be 12 amps. And the way you set that out is you say the reading on A1 is equal to the total current, is equal to I total, okay, which we can then work out. I total is the current in the first branch plus the current in the second branch. Didn't give myself enough space for this, sorry. So that's 3 amps plus 9 amps, which is 12 amps. Okay, so the current over here is 12 amps. Question 7, determine the reading on A4. Okay, so the current came out the battery. It was 12 amps. It split into 3 amps and 9 amps. Okay, so it splits, and here it comes back together again before it goes through that ammeter. So the 3 amps here and the 9 amps there will add together again at this point to form 12 amps again. So again, we're going to say A4 is equal to the total current, which is 12 amps. Okay, question 8. Oh, this one's tricky. I'm actually going to need more space for it. I'm going to give myself more space quick. Okay, so question 4, we want to change the total resistance in the circuit. Okay, so currently the total resistance is 3 ohms, right? Now I want to change the total resistance in the circuit to be 1.2 ohms. That is possible. It is possible to decrease the resistance in a circuit by adding resistors in parallel. Remember that. Okay, so we're going to add a resistor in parallel to bring the total resistance from 3 ohms down to 1.2 ohms. And the question here is, what size resistor must I add in parallel? So I'm adding another branch on here. Let's gooi them right through the middle. Okay, I'm adding another branch here with another resistor to try and bring down that total resistance. What must that resistor's resistance be? Okay, now we know that to find the total resistance, we say that's the sum of the resistance. Sorry, to find the total resistance, we say 1 over R total equals 1 over the sum of the individual resistors. Now, so far we've only had 2 resistors, but now we're putting in a third one. So it's R1 plus R2 plus 1 over R3. Okay, now we can substitute in what we know. Okay, so we know our total needs to be 1, 2. So I'm moving over here, so it's going to be 1 over 1, 2 equals R1, they told us in the question was 12 ohms, so it's 1 over 12, plus R2, they told us in the question was 4 ohms. And R3, this is the new resistor that we're adding. We don't know its resistance. You can say 1 over whatever you like, 1 over X. I'm going to go 1 over X. I think in your worksheets I just called it R. I called it R new. Okay, I'm just going to call it X now. Okay, so we go ahead and add them, and we are trying to determine the value of X here. Okay, so that means we need to isolate X. We're going to bring these two fractions across and subtract them. So we're going to have 1 over 1, 2 minus 1 over 12 minus 1 over 4 equals that 1 over X. Okay? On your calculator, you can go ahead and work out what that part equals, the difference of these 3 fractions. You can go ahead and work out what that equals. What did I get? 1 over 2. Okay? So I get that 1 over 2 is equal to 1 over X. I'm going to move across here now. I'm running out of space. Can you even see that? Yes, you can. Okay. So 1 over 2 equals 1 over X. And now the last step is to invert that. So we're going to say then that X is equal to 1 over 2 to the power of minus 1, which means X is equal to 2 ohms. So if I want to bring the total resistance of this circuit down from 3 ohms to 1.2 ohms, I need to add an additional resistor in parallel, and that resistor has to have a resistance of 2 ohms. Okay. So yeah, it can be a little bit tricky. I think that the worst thing really is just remembering how everything is affected. Remembering how, if this is in series, how does it affect each of the 3 things? If it's in parallel, how does it affect each of the 3 things? And then also always remember Ohm's law is an option. Okay, don't ever forget Ohm's law is an option. Just make sure that you can use it. You can only use it if you know 2 of the 3 variables. Okay, yeah, so that's it. Yeah, the rest I'll chat to you about on WhatsApp.